So let's have a look. We are halfway through. Let's have a look at how do we model the inverter. And you'll see it becomes a little bit easier. Or maybe I should, I will take the solution. So we'll just walk through the solution. Okay. So we've modeled the array, the power output of the PV array. Now we need to model the power output of the inverter. So the power output of the inverter is not exactly the same as the power of the PV panels. That is because there's losses occurring inside the inverter, and there are two major types of losses that can occur or occur. The first one that always occurs are the conversion losses. So a power converter has some efficiency, which is variable. It's not an ideal converter, or there's always thermal losses and switching losses occurring inside the inverter. How many they occur will depend, as we'll see, on several factors. The other thing that can occur on an inverter is clipping, and that is true especially if the input power, so the PV array is oversized. So we have a 5 kilowatt PV array and a 3 kilowatt inverter. Of course, the inverter will not output 5 kilowatts, even if the panels can generate that. And that those 2 kilowatts are being clipped, and those we consider to be losses. So let's take a concrete example. In the Enerpost system, there's 2 types of inverters. Both are from Delta. They are from the same inverter family as the RPI family, but they are rated at different powers. So for inverter 1 and 2, connected to the northeast building, these are 10 kilowatt inverters, and the maximum AC power is actually 10.5 kilowatt ampere. These are 3-phase inverters, each have 2 independent MPPT trackers and have a weighted efficiency of 98%. If you look at the manual of the inverter, you'll see it has an efficiency curve of the inverter. That means that the conversion efficiency, so the ratio of the output power versus the input power, is not constant. It depends on the operating point or the load of the inverter. So the main factor that determines the efficiency is what is the power or the loading of the inverter. And this is given as output power or input power. But it's basically a measure of how much energy is passing through the inverter. Now, inverters are designed to operate at high load, so they will have high efficiency at high load. Whereas if you take an inverter and you operate it at very low power, the efficiency will start to drop because it's not designed to operate there. The other factor that can influence the efficiency, the conversion efficiency of an inverter, is the voltage, the input voltage you are operating it at. So inverters are designed to operate at a nominal voltage where they will have the highest efficiency. And in this case, is this orange curve. However, if you make you put too few panels or too many panels in a string, and the string voltage is, in this case, lower than 600 volts or higher than 600 volts, then the efficiency will be slightly different. So in this case, the worst case is if you have too low voltage at the input of the inverter. So you don't put as many panels in series, and then maybe you put more panels in parallel, or it really depends on the type of panels you have, what is the voltage of the panels, how many you put in series. So if you don't optimally select your panels and inverters, you might end up with some string that has 400 something volts, and that will make it the inverter operate with about 1% less efficiency than if you would make a 600 volt string. So in order to model our output power of the inverter, we need to model this efficiency curve of the inverter. And then if you multiply the input with the efficiency, then you get the output. So if we manage to model this, we have basically made a model of the inverter. Now the second inverter used is this Delta 15A, which is a 16.5 kilowatt inverter that is used for on the southwest roof. So this is slightly larger, and then you can see it has slightly different efficiency curve, but it kind of has the same average efficiency. So this EU efficiency, it's a weighted average efficiency that kind of takes this curve and weights it to how long during the year is the inverter typically operating at that loading. So this EU efficiency is a average weighted efficiency for European countries, or for the European climate. Let's say that. But you can see they are quite similar in the weighted efficiency, even though the curves look slightly different. So the simplest model that we can make for an inverter is to make an inverter based on the weighted efficiency and accounting for the clipping. So if your input power is lower than the rated power of the inverter, then you just need to multiply it with the efficiency and then you get the output power. However, if the power, the input power is much greater than the rated power of the inverter will not be able to output that because it was only designed to output a certain level of power, after which the components get too hot and then they degrade faster. So what inverters will normally do whenever the input power is greater than the rated input power or the rated output power, it will start limiting. And the way it limits that is by shifting the maximum power point, the operating point of the PV array away from the maximum power point. So it's operating at a lower input power. And all modern PV inverters do that to avoid overheating, basically. So for the simplest model, we just need to know what is the rated AC power of the inverter and what is the weighted U efficiency. So let's see how good this model like this is. So what we will do, we will model the AC power of inverter 1 based on measured DC power for inverter 1 for these 2 weeks. So we'll first, okay, I need to disconnect some sessions. So I'll disconnect this one. And yeah. Let's see how this goes. Okay. We've initialized our environment, and here we don't need weather data because we will use as input, we will use the measured values at the inputs of the inverter. So we only load those for this model. Then we need to determine the weighted efficiency and maximum AC power of the inverters. And if we look at their data sheet or what is written here, we see the U efficiency for the first one, for inverter 1 is 98, and the maximum AC power is 10.5. And this is what we put in as parameters here. And then we can do the same for the other one if we want to. Then for implementing the model, we'll use a function, and we use a function so it's reusable. We can reuse it in different places without repeating the code. And the function will have as an input the DC power, the efficiency, and the maximum AC power of the inverter. And then we just basically we implement this equation here. We multiply the DC power with efficiency, we get a temporary AC power. We do a bit of cleanup if we get negative values. And then for all the values that are larger than the limit of the inverter, we'll limit that. So we kind of implement the clipping. Then we just need to apply it. So what is this PDC? Well, for this inverter, it has two inputs, two MPPTs, if you remember here. Inverter 1 has MPPT1 and MPPT2. And actually, we had it in exercise 2 as well. If you remember, where was it? Inverter 1 has MPPT1 36 modules and MPPT2 18 modules. And then we have measurements from MPPT1, and we have measurements from MPPT2, and then we have the actual AC output measurements. So we will use these. We add the two DC measurements together, so we get the total DC input power of the inverter. That will be the input to our model, and then we provide the weighted efficiency and the AC max AC power, and then we compare it with the measured values. I think I need to run this. So we run this. And then if we compared the simulated with the measured AC power, we get very, very good correspondence. So let's see in terms of efficiency, what is the difference between the actual efficiency of the inverter and the model efficiency. So in this case, we assume a constant efficiency of 98%, whereas the actual efficiency or the operation efficiency we can calculate by dividing the output power with the input power. So if we do that and we plot, in blue would be the actual operating efficiency of the inverter, and in red is the assumed efficiency of our model. We can see that for most of the operating range, they coincide very well. So this inverter has a very linear efficiency characteristic, which is very good. That makes modeling very important, very easy. And we don't see a lot of voltage dependency here. So implementing, there's models that can also account for this variation, but it's not really necessary for this system as far as we can see from modeling it. The only differences that we see are at low power. So where the linear efficiency or the assumed efficiency starts to deviate, because as the loading of the inverter gets very small, the efficiency starts to drop drastically. So the only kind of model limitations would be here, but at this point also the energy is very low. So we are not losing a lot of accuracy in that place. Now PV Watts also has some simple models for modeling the inverter, and a very good one is the PV Watts or the PV Watts multi. The difference between these two is the multi can take inputs from several MPPTs. Let's have a look at this one. The equation is slightly different for the PV watts model than what we are using. They use a nonlinear efficiency model. We use a linear assumption. But it's still a single input model where you just need to provide the rated power, in this case, the DC rated power, and the weighted efficiency of the inverter. And then the input is the measured or the DC or the power at the input of the inverter. This is the only input variable. These are parameters. So it's a single variable model. And if we run this one, we just need to, if we use the multivariant, we provided the measured DC power from the two MPPTs plus the DC rated power of the inverter, and we obtained that by multiplying the AC rated power with efficiency, and then the weighted efficiency of the inverter, and then we get something like this. And we can see our model is in orange, the pvlib model is in green, and the measured is in blue, and they coincide fairly well. And then if we calculate the efficiency of the PV watts model here in should be orange, we can see that the PV model, since it's a nonlinear efficiency model, coincides very well with the measured efficiency. So it's, for a simple model, it's extremely accurate. Now there's other PV inverter models in pvlib. Some of them also account for the input voltage. For this type of inverter, it is not necessary. Also, since we are using a simple PV array model that only estimates power, we cannot use a inverter model that uses voltage as an input. So we would need to also use a different, more complicated PV array model to use one of the other inverter models that accounts for the voltage dependency. For this inverter, it's not a problem because the variations in voltage are not very big on the array side, and there's not a very high voltage dependency on the inverter for the voltages of operation. So either if you are using this model, or if you are using the PV watts model in pvlib, you are very close to the real value. So implementing a more complicated model is not necessary in this case. So I think we are ready for a break, or at least my voice is.
Yeah.
So if you have questions, put them in the chat. Otherwise, let's take a 10-minute break, and then we'll finish with the last part of the workshop, which is putting everything together. So let's be all back at 10 minutes after 2. Thank you.
Sergio, I have just a question before.
Yeah.
We can observe in the measured data efficiency that are above 1. It's very strange, no, for the inverter.
Yeah, so it's either this inverter has surpasses the laws of thermodynamics, or there is something wrong in it's usually, it can be that the measurements are not very well synchronized between the input or the output. That sometimes can happen, but it's just a data artifact. It's either the input is not synchronized with the output, or there's some sensor errors, I would say.
Thank you.
Yeah, but for sure it's not an inverter that is more than 100% efficient. Yeah,
I
but
believe it immediately.
I've seen this in almost all inverters have, and this is just because the measurement system of the inverter is not, laboratory grade. It's a commercial inverter, so yeah, it will have some data issues. Okay, So let's take a 10-minute break.